Hi guys, we will solve some questions from this new worksheet, which is worksheet 10. So I will solve the questions which are marked by blue and 2 and 3. All right, so for the first question, we will determine if the given series is convergent or not. So in the first part, we are given the series. All right, so for, we will apply integral test. So let me recall that. Right, so we have, first assume that we have a sub n, which is a sequence of positive terms. And let's assume that we have some function, right, f, whose image, the image of the natural number n is a sub n, right? And assume that f is continuous, positive, decreasing for all n, but sorry. Okay. This is not, let me write like this. So we have f of x for all x greater than some n. Okay. So in this case, we conclude that the series a sub n, starting from this uppercase n till infinity, and the integral from n to infinity again, f of x dx, are both convergent or both divergent. Okay. So it's enough to find some or define some function f, and we will compute the integral of this function. So if the integral converge, then the series also converge. Otherwise, it will diverge. So let's define some functions. So f of x will be x squared e to the minus x cubed, because we want to define this. We want the image of natural numbers to be the terms in the series, right? So we need to define that function with respect to that terms. So that's why we define that like this. So this is continuous, it's obvious on the real numbers because we have a polynomial and e to the something, so they both convert continuous. And remark that f prime of x is equal to 2x e to the minus x cubed minus 3x to the 4 e to the minus x cube. So let's write it as in this form. So if we equalize it to 0, we find the critical points, which are x equals to 0, or either x equals to 0 or this is equal to 0. So it gives x equals to third root of this. Okay. So what do we have? We have f prime. So the roots are 0. So it's increasing and decreasing. Just take any point from this interval, for example, any point from this interval, and compute if the function gets the sign of the values of the function gets. Okay, so we determine that after this point, after this critical point, the function is decreasing, right? So on this interval, it's decreasing. And we see that the natural number 1 is greater than this, so we can conclude that f of x is decreasing and it takes positive values on this interval. Okay. So before 1 we have only the natural number 0, right? So we don't care about this number, we care about natural numbers. That's why I took this interval. Okay, so now we need to compute the integral of this function. Here n will be equal to 1, right? So from 1 till infinity, we need to compute f of x dx, the integral of f of x. So what do we have? We have the definition of f was this, dx. So it's equal to, let's write t. So we need to compute this. X. Right. Now we have this t. If we substitute here u equals to minus x cubed, we will get du equals to minus 3x squared dx. So we just plug these ones into the integrand. We get this. Right, so by computing this limit, first the integral, I mean, what do we get? We have minus e to the u over 3, just plug u equals to minus x cubed, so we get this from 1 till t. Okay, so now we have, just plug x equals to t, then x equals to 1 and subtract them, so we will get minus e to the minus t cubed over 3 plus e to the minus 1 over 3. So when we plug t, if t is approaching infinity, we will get 1 over 3e, right? Why? Because, right, color. So this is just a number. So look at this part. When so it's equal to e to the 1 over e to the t cube, right? When t is approaching infinity, this will be what? infinity. So we will have 1 over infinity, which is equal to 0. So we will just have this number, which is equal to 1 over 3. Right now, we see this is just a number, right? So it means the integral of f on this interval, 1 comma infinity, is convergent. It means the series by the integral test, right? It says that if this is convergent, then so is the series. So using the integral test, we see when n equals to 1 till infinity, and n squared e to the minus n cubed is convergent. When n equals to 0, it's not defined, right? So we're done. Okay, in the part C, we're given this series 1 over n squared plus 6n plus 30. Now for this one, we will use limit comparison test. So observe first the limit of this one. One over n squared, it's equal to the limit of this one. So it's equal to 1, which is greater than 0. And we know that this series 1 over n squared, which we plugged here, is convergent because it's a p series and p is equal to 2. So as 2 is greater than 1, right? This is always convergent when p is greater than 1. So it's convergent. Then the limit comparison test says that the given series is also convergent. Hence we're done by limit comparison. Comparison test. The given series is also convergent. Now by in the part E, we're given this series n minus 1 over n. Let me check again. N squared square root of n. Now remark that we have this n minus 1 over n squared square root of n is less than this one, right? The denominators are the same. Okay. Denominators are the same, and this one's numerator is greater than the other one, so it's greater than the previous one. And we can write this if we simplify them. We will have n to the n times square root of n, which is equal to n to the 3 over 2, right? And we know the series, this series, when we have this, is convergent. Again, p is greater than 1, so it's convergent. Then and we have these terms which are less than these ones. Then by comparison test, as this is convergent, by comparison test, the given series is convergent, right? As we found something greater than the given one and which is convergent, then the previous one, the less one, is also convergent. Now in the part F, we have the series arctangent of n over n to the 1 over 2. So observe, we have arctangent n over n to the 1 over, 1 comma 2, and it's less than this one. Why? Because arctangent is bounded by pi over 2 above and it's bounded by minus pi over 2 below. So we have this inequality for all n greater than or equal to 1. And similarly, we have this series 1 over n to the 1 comma 2. Sorry, not 1, pi over 2. We can write this like as in this form. And this is convergent because we have something greater than 1 as the power of m. Hence, it's convergent. By it, I mean this series, this given series. By the same test, by the comparison test. Now, part M, we're given this. Okay. Now we will use the ratio test, sorry, the root test. So we need to compute the limit of this square root of the nth root of, sorry, this. Here we are using the root test. So this is equal to this limit, which is, and this you should know, it's equal to e, which is greater than 1. So by the root test, it's divergent. It's convergent when this limit is less than 1. Now the last part, we're solving from this question. We have 2 minus 1 to the n over ln of n. Right, we will use alternating series test here. Okay, check that. Alternating series test. So let me recall that. What does it say? Okay, the series we have now a series of this form, minus 1 to the n plus 1 times a sub n converges. The test says this, it converges if we have first an, the terms of this series are positive for each n, and the second one, the second assumption is this, or condition we may say, is non-increasing for all n, which are greater than some n, some uppercase n, right? What does that mean? That is for all n greater than uppercase n, a sub n is greater than a sub n plus 1 or equal to n plus 1. And the third condition is this, an is convergent to 0 when n is approaching to infinity. Now we need to check these 3 conditions to determine if the series converges. So let's check. First of all, here an is what? An is equal to 1 over ln of n. When n is greater than 1, it's positive. They are all positive, so this is checked. And the function, the logarithmic function is increasing. So 1 over ln, which is a sub n, is a non-increasing function, right? As ln of n is increasing, then a sub n, which is 1 over ln of n, is non-increasing. So this one is also checked. Now what about the limit of a sub n? Limit of a sub n when n is approaching infinity, we have this limit 1 over ln of n. Ln of n is approaching infinity when n is approaching infinity, so we have 1 over infinity, which is equal to 0. So this is also checked. Hence, by alternating series tests, the given series in the Q is convergent. All right. Now we're done with the first question. So we will solve this one too. Right, we will assume this equality. We will assume this series of 1 over n squared is equal to pi squared over 6, and we will try to find these ones using that fact. Okay. So not. So we're given this one, this equality, pi squared over 6. So I will show only the second part. Here we have this and plus 1 squared. Okay, we're given this. We will find the sum using this fact above. So let's first write a few terms of this series. Just plug, for example, n equals to 3, you will find 1 over 4 squared. Then n equals to 4, you will get this. N equals to 5, get this. So we can write it as in this form. But here in this sum, we don't have these terms, so we need to get rid of them. Right, so we have equality. Now we know the first sum, this sum, is equal to pi squared over 6 by the given fact. So we have this minus, we just need to find that sum, which will be equal to this. Hence we're done. Right, the first part is much more easier, so I leave it. Now the third question. Right, we will find the values of k so that this given series is convergent. Now, so we're given this n factorial squared over this. Right, we will find the values of k, as I said before, so that the series is convergent. Now we will use the ratio test now. All right, so we need to find this limit when n is approaching infinity. So we just find here a sub n is what? It's the terms of the series. Okay, we just plug n equals to n plus 1 first, then n equals to, then just a sub n, we will divide them. So we find by computing that squared over k times this, and maybe this one is more clear. So we have this over this one. Okay, now what do we have then? Limit of this. We have n plus 1 times n plus 1 squared n k factorial over this k times this minus 1. Maybe I can write it here. Then what? Times kn plus 1 times kn factorial. We have this. Now, if we simplify these ones, this one and this one, they are equal. Then what do we get? Limit of n plus 1 squared above in the numerator, and the whole thing, the same thing I will write. Minus 1 times the last term. Okay, so we have this. We need to examine the cases. So if k equals to 1, what do we have? Limit n is approaching infinity. Above we have n plus 1 squared over. When k equals to 1, we have n plus 1 in the denominator, right? Because each term in the denominator, each term will give us n plus 1. It means, so, but they should be decreasing, right? This one is less than this term, for example. This one is less than this term. That's why we wrote like this, okay? If each term is equal to n plus 1, then we have only one term in the denominator. Now, but this is infinity, right? So the series in this case is divergent. Then it means k cannot be equal to 1. Now, if k equals to 2, what do we have? Again, write the limit. We just plug here k equals to 2. So what do we have? N plus 1 squared again over 2 times n plus 1, the first one, then 2 times n plus 1 minus 1. Now it's equal to n plus, let me write clearly, n squared plus 2n plus 1 over, here we have 2n plus 2 and here it's equal to 2n plus 2 minus 1, it's equal to this. Now if you compute this again, 4n squared plus 2n plus 4n, we get 6n plus 2. So we have 4n squared plus 6n plus 2. Thus the limit is equal to 1 over 4. So the series in this case is convergent. Okay. Now, if you take any value of k greater than 2, you will have in the denominator, you will have something greater than the numerator. By greater, I mean the multiple of the highest power of n will be greater in the denominator, so the series will convergent. Thus, for any for any k greater than or equal to 2, the series is convergent, right? Because in the numerator you will have only n squared, right? So, but when you take any value of k greater than 2 or equal to 2, you will have some power of n. It may be n squared, as in this case, but if, for example, k equals to 3, you will have, I guess, n cubed or something. So the power of n in the denominator will be greater than the numerator. So the limit will be equal to 0. So it means for any value of k, which are greater than or equal to 2, the given series is convergent. So we're done. Okay, this was the last question of this worksheet. See you next week.